Hello everyone, we are from Group 5 and we are going to present the X-ray spectroscopy. So, without further ado, let's get started. This is our group detail, so basically there's nothing to talk about here. So, let's not waste our time here, shall we? First, let us talk about the X-ray spectroscopy. The X-ray spectroscopy is a spectroscopic technique for characterization of material by using X-ray excitation. There are two types of X-ray spectroscopy. The first one is the energy dispersive X-ray spectroscopy, the EDXS. The energy dispersive X-ray spectroscopy is the spectroscopic method that using the principle of excitation of electron, which is basically similar to what we learned before, such as the UV visible spectroscopy, the AAS spectroscopy, and etc. The second spectroscopy is the wave dispersive X-ray spectroscopy, the WDXS, which use the principle of diffraction of the ray. So, in characterization of polymer, we use the X-ray scattering, which is a wave dispersive X-ray spectroscopy, to determine the spatial arrangement of all the atoms in the polymer. Before we move on to X-ray scattering, let's get familiar with Bragg's law. Bragg's law was proposed by Lawrence Bragg and his father, William Henry Bragg, in 1913, who found that the crystalline solids will produce intense peaks of reflected radiation at certain specific wavelengths and incident angles. For a crystalline solid, the waves are scattered from the lattice planes separated by the interplanar distance d. When these scattered waves interfere constructively, they remain in phase since the difference between the path lengths of the two waves is equal to n integer multiple of the wavelength. The path difference between two waves undergoing the interference is given by 2D sine theta. So if you look at the picture at bottom right, there are two rays hitting two atoms that are arranged parallel to each other. So you can notice that the ray at the bottom have a longer path length compared to the upper one. So they have a path difference that is equal to d sine theta. Since both rays are in phase, their scatter wave also will have the same path difference. Thus, the path difference total will equal to 2d sine theta. A diffraction pattern can be obtained by measuring the intensity of scattered waves as a function of scattering angle, which you can see it as the picture at the upper right. So in general, the constructive interference can be described as the equation 2d sine theta equals to n lambda, where n is a positive integer and lambda is the wavelength of the incident wave. If n is not an integer, that means it is a destructive interference, and the waves are not in phase. Now, let's move on to X-ray scattering. There are two types of X-ray scattering that can be used to determine the crystalline structure of polymer, which are the wide-angle X-ray scattering, the WAXS, which is an X-ray diffraction method, and the small-angle X-ray scattering, the SSCC. They are based on Bragg's law, in which the distance from sample to detector is either shorter or longer to make the diffraction maximum at larger or smaller angles. So they use the principle of Bragg's law in which the X-ray will hit the polymer and the polymer will undergo constructive interference and emit the scatter waves. The scatter waves will create the diffraction pattern, in which the same as the slide before. So the scattering intensity is plotted as a function of the 2 theta angle. Every crystalline solid has a unique pattern of D-spacing, which is known as the powder pattern, which is a fingerprint for that solid.
The method of X-ray spectroscopy. X-ray spectroscopy is used to determine the spatial arrangements of all the atoms in polymers. How the X-ray spectroscopy is functioned. X-rays are generated in cathode ray tubes when high energy electrons impinge on metal target like copper. When the X-rays are focused on a polymer sample, there will be two types of scattering will occur. Next, types of scattering. There will be a difference in scattering for crystalline and semi-crystalline sample. If the sample is crystalline, X-ray scattered coherently, which is wide angle measurement. There is no change in wavelength and also no change in phase between the incident and scattered rays. If the sample is semi-crystalline, the X-rays scattered incoherently, which is small angle measurement. Now, there will be a change in wavelength and also a change in phase between the incident and also the scattered rays. This is how X-ray scattering techniques looks like. We can see at the left side is the wide angle scattering, which called as WAX, wide angle X-ray scattering, and on the right side we can see the small angle scattering, which called as SAX, small angle X-ray scattering. For the wax is consists of a series of concentric cones arising from scattering by the crystal planes. Wax is also recorded as concentric rings on the X-ray plate superimposed on a diffuse background of incoherent scatter, while for the sacs are very diffuse. There is another way to present the 2D scattering spectrum of the polymer, which is we can make a plot of intensity versus angle of scattering. The patterns and intensity of X-ray scattering through visual examination and mathematical modeling interpretation can provide us two information. The first information is the polymer morphology and the second information is about the structure.
Well, let's move on to the examples for X-ray diffraction. We know that polymers come in many forms, including highly crystalline, semi-crystalline, microcrystalline, or amorphous. The first example is microcrystalline cellulose. The most common form is used in vitamin supplements or tablets. Figure 1 shows SRD patterns for microcrystalline cellulose. In MCC, exhibited a sharp diffraction peak between 19 to 22.6 degree. It is indicating that microcrystalline cellulose has a crystalline structure. The crystalline patterns will show many sharp peaks due to the atoms are very carefully arranged and high symmetry. The second example is polyethylene terephthalate. PET is used especially in containers produced for storing and carrying food and liquids. PET is known as crystallizable polymer because of its regularity in chemical and geometric structures. It is either in semi-crystalline state or in the amorphous state. X-ray diffraction pattern of PET shows the presence of the intense and broader peak in the range of 2 theta from 20 to 30 degree, which can be assigned to the semi-crystalline structures of PET polymer as shown in figure 2. Semi-crystalline polymer demonstrate that the XRD pattern shows two-phase morphology, crystalline and amorphous state. In conclusion, we can say that PET has sharp peak due to the highly oriented crystal plane.
Now, we have reached the end of our presentation. We appreciate your attention and we apologize for any mistake we made. Kindly remember to do the question, alright? Thank you.